children. So in this session we will learn about the structure of NaCl. This is the part of solid state chapter only, and there are four structures of four type of solids. So there are ionic solids, covalent solid, metallic solid, right? So the type of solids we have studied earlier in the beginning of the chapter, and so we have the structure now of each or type of solid. Their structures we have to study in detail. So structure of sodium chloride. Sodium chloride is a ionic solid and its structure goes on like this. So structure of NaCl, you will say that NaCl molecules, they arrange themselves in CCP or FCC arrangement. CCP or FCC is same thing, and CCP means cubic close packing and FCC means face centered cubic arrangement. So if it is asked what is the type of unit cell in NaCl, you have to say it is CCP or FCC arrangement. This is the type of unit cell in NaCl. Out of Na and Cl ions, it is the chloride ions which arrange themselves in CCP way. So this we have studied earlier, that out of the cation and anion, it is the anions who arrange themselves in a particular way, HCP or CCP. So here chloride ions arrange themselves in CCP way. When they arrange themselves in CCP way, in that way, they come at the corners and at the face centers. Sodium ions are the cations. So cations, as we have studied earlier, they occupy the voids generally. So sodium ions in NaCl structure occupy the octahedral voids. Now when it occupies the octahedral voids, it comes at the body centers and at the edge centers, right? Further, the radius ratio of sodium and chloride ions has been found to be 0.525. Now this is not an ideal situation for sodium ions to occupy octahedral void. We already have studied that if the radius ratio is 0.414, the radius ratio of positive and negative ion, that is the cation and anion, if it is 0.414, then the particular ion will occupy the octahedral void. But here you can see the radius ratio is more than 0.414. It is 0.525. So this is not an ideal situation for NaCl to occupy the octahedral arrangement or for sodium ions to go in octahedral voids. So to arrange or to adjust sodium ions in octahedral voids, the NaCl possess expanded FCC lattice, in which the chloride ions, they slightly open up to accommodate sodium ions, right? So what do you understand from here? That the size or the radius ratio is 0.525, while if the cation has to go in octahedral void, its radius ratio should be 0.414. Since here the size of sodium and the radius ratio of sodium and chloride ions is more than 0.414, so chloride ions have to slightly open up to accommodate the bigger size sodium ions in its octahedral void, and because of this only NaCl is also said to have expanded FCC lattice. Further, NaCl structure, the coordination number is 6:6. What does this mean? This means that each sodium ion is surrounded by 6 chloride ion, while each chloride ion is surrounded by 6 sodium ions, right? This is what about the coordination number of NaCl. Now we come to the calculation of sodium and chloride ions per unit cell. We want to know how many sodium and chloride ions lie in one unit cell of NaCl. So here is the calculation of chloride ions, number of chloride ions. Now you know chloride ions occupy the corners and the face centers. So the number of chloride ions, because they occupy the corners and there are 8 corners, contribution of each is 1/8. Plus there are 6 face centers, contribution of each is 1/2. So that makes it 4. So the total number of chloride ions in the structure is 4. While the number of sodium ions, now sodium ions goes into octahedral voids, and in that way it comes at body center and at edge centers. You remember there are 12 edges in a cubic unit cell, right? So there are 12 edges, and the contribution of each edge, particle at each edge, is 1 by 4. So 12 into 1 by 4 plus the sodium ions are also at body center. At body center, the contribution is total 1, so that again makes it 4. So the number of chloride and sodium ions per unit cell is 4. So there are 4 sodium and 4 chloride ions in one unit cell of sodium chloride. Then this structure of NaCl is also said to have rock salt structure, or you can say the another name for its structure is rock salt structure. So this is very important part, and so many times the questions on this NaCl structure have come in ISC examinations. Now we come to the structure of covalent solid. Diamond and graphite are examples of covalent solids, and we are going to study their structures in detail. Now for diamond, diamond is very hard. You know, it is the hardest substance known. And why it is hard? It is hard due to its three-dimensional network of covalent bonds. So diamond is an allotrope of carbon, you know this. So it is made up of carbon atoms. And how are the carbon atoms arranged in diamond? Through covalent bonds. The covalent bonds form a three-dimensional network of very strong covalent bonds, because of which diamond is very hard. Each carbon is tetrahedrally linked to 4 other carbon in diamond, and the hybridization of each carbon is sp3, right? So there is no free electrons in diamond, so it does not conduct electricity. You know that the diamond or any substance can conduct electricity only when it has free ions or free electrons. So carbon do not conduct electricity because it does not have free electrons. Let us see why it does not have free electrons. You see the structure of carbon. The atomic number of carbon is 6, and this is the atomic configuration of carbon: 1s2, 2s2, 2p2. So the last shell is second. In its second shell, the s and the p subshells have 2 and 2 electrons. When the carbon get excited, one carbon from 2s jumps to 2p, right? So this way now there are 4 unpaired electrons in each carbon. Now these free electrons, unpaired electrons, which have to form covalent bonds, since each carbon is bonded to 4 other carbon through single covalent bond. So these 4 half electrons have to be utilized in formation of single covalent bonds. So before the formation of bonds, you know, they undergo hybridization. They mix up their energies, and the hybridization is sp3. So 1s and 3p electrons, they hybridize together, right? The orbitals, they hybridize together, and the hybridization is sp3. Now each carbon has 4 sp3 hybridized orbitals. You see, in the last shell there are 4 electrons, and all 4 are involved in sp3 hybridization, and later on they are involved in the formation of single covalent bonds with other 4 carbon atoms. So since there is no free electron left, so diamond does not conduct electricity. So this is about the structure of sodium chloride and diamond. Let us come to the structure of graphite. Now the next is structure of graphite. Now in graphite is also an allotrope of carbon only, so it is made up of carbon. But what is the arrangement of carbon here? It is different from diamond. Each carbon in graphite is attached to 3 other carbon, while in diamond each carbon is attached to 4 other carbon. And in that way, all the carbon, each carbon attached to 3 carbon, forms planar hexagonal rings of this type. So you see, each corner of the hexagon is carbon, and you see each carbon is linked to 3 other carbon. If you suppose this is the carbon, then see it is attached to 3 other carbon in this way, right? So this way each carbon is attached to 3 other carbon, and planar hexagonal rings of these carbon are formed, right? Hybridization of carbon is sp2 in diamond it was sp3, while here carbon is sp2 hybridized, right? Now graphite is soft, is very soft, and it generally is it is used as a lubricant, getting it? So why it is soft? And why diamond was hard? Diamond was hard due to strong covalent bonds. Now we will understand why graphite is soft in nature. So we see that each carbon is attached to three other carbon and forms planar hexagonal rings. These planar hexagonal rings, they form layer over each other. Now these layers of hexagonal rings, they are attracted to each other through weak van der Waals forces. Because of these weak van der Waals forces between the layers of the hexagon rings, the graphite is soft. So you see, if the bonding is strong, the substance will be hard, while if the bonding is weak, the substance will be soft. So it is because of these weak van der Waals forces that graphite is soft in nature. In another way also it is different from diamond. It conducts electricity, right? But diamond does not conduct electricity. So it conducts electricity because of free electrons in it. Now how does it have free electrons? This we can understand by understanding its hybridization. You see carbon, the outermost configuration is 1s2, 2s2, 2p2. In excited state, one of the electron jumps from 2s to 2p and all the 4 orbitals are half filled now. Out of these 4, 3, 1s and 2p are involved in hybridization sp2, while the fourth is left unhybridized. It is this unhybridized orbital carrying a free electron in it which is not involved in any bonding, and because of this free electron, graphite can conduct electricity. So the main points in the structure of graphite is, you have to understand the reason why it is soft, why it does not conduct electricity, the hybridization and all in it. Now the next structure, we come to the structure of metallic solid, that is copper. For copper, we will understand that it arranges itself in FCC arrangement. The cubic unit cell it crystallizes in is FCC, that is face-centered cubic arrangement. Since the unit cell is FCC, so the metal ions, they occupy the corners and face centers. They are present at the corners and at the face centers. You remember that coordination number of each metal ion in copper metal is 12. This means each metal is surrounded by 12 other metal ions, out of which the 6 are in one plane and the 3 are present above this plane and the 3 others are present below this plane. So in total, each metal ion is surrounded by 12 other metal ions, in which 6 are in one plane while 3 are above and 3 are below this plane. So this is only that you have to study in structure of copper metal. In the next session, we will understand and learn about imperfections in solid. Goodbye.